Hi, and welcome to Allen High School's discussion of the properties of liquids and solutions at the pre-AP level. We're finishing up our unit with a quick discussion of colligative properties. In the past, we used to do calculations with these, but for now, we're going to discuss these qualitatively. I just think it's so important because it's so practical. You don't always get to see the practical applications of chemistry, and I think this is one where it's very obvious. Now, a colligative property, it has that word, kind of a hint of the word collective in it. And a colligative property depends only on the number of particles in the solution. Not necessarily the identity of the particles, but the count. So we're counting particles in this case. Now, when we add a solute to a solution, we are always going to see an elevation in the boiling point and a depression in the freezing point. It's kind of like right now in the midst of winter, if you hear all these people from the Midwest and all the snow and they're really tired of it, the freezing is kind of depressing them. And if we could just ship them all to, Destin, Florida, the heat wave there would elevate their moods. Okay, so if you add, for example, salt, which we tend to do, people think that adding salt makes water boil faster. It doesn't. It actually takes a teeny bit longer to boil. What it does is it causes water to boil at a higher temperature. And up north, again, where they're having all of these snowstorms right now, if they put salt on the roads, we don't tend to do that as much. Sometimes they'll throw sand on the roads to help with, friction and prevent sliding. But when you put salt on the roads, you lower the freezing point. So it'll melt at a lower temperature, and hopefully that ice will melt sooner and become a little safer. Okay. Now, I want to draw you a picture of this. I think that it would help a little bit and give you an idea of the particles involved. So if I drew this line here, let me see if I can get these lines a little wider. It'll help on the next ones. Okay, so I've got a line here. If this is my pure solvent, so pure solvent, this is its boiling point, this is its freezing point. Now, remember earlier when we were dissociating particles, we were counting the number. We had this random number I. So let's say I is equal to 1. That means that one particle went into the solution, and all covalents are 1, because covalents don't dissociate into ions. So what will happen then is that we will elevate the boiling point, so that'll be a little higher, and will depress the freezing point. Okay, so now if you notice here, my boiling point went a little higher, my freezing point went a little lower. Now let's say I is equal to 2. So now we have, it's going to go higher still, and it's going to go lower still. So do you see how this kind of spreads out as we go? So the higher, it becomes more elevated, and it becomes more depressed. So a good example of this would be NaCl. Sodium chloride breaks into a sodium ion and a chloride ion, so I is equal to 2. And then if we did I equals to 3, I hope by now you're getting this pattern down. And here we would have I equal to 3. In this case, you may have something like calcium chloride. And again, we have a higher elevation and a lower depression. Now, if you had to pick, we have a calcium ion, and we have a chloride ion and a chloride ion. If you had to pick which one you wanted to use on your roads in the winter, I would certainly choose calcium chloride. Now, we don't want to be eating calcium chloride, so I certainly wouldn't choose calcium chloride for my boiling point. Now, I'm not sure what they use on the road. I forget. It might be magnesium chloride, but the point is they're going to pick a salt with a higher I. So let's take a look at this. Which substance, I equals 3 or I equals 4, is going to have more change in the freezing and boiling point? And the answer is I equals 4, because as you increase I, you increase the boiling point elevation of the new solution, and you decrease the freezing point because it's more depressed of your new solution. And it is magnesium chloride there. So magnesium chloride is used as opposed to sodium chloride because magnesium chloride has I equal to 3. Sodium chloride has I equal to 2. So the freezing point for the magnesium would be less than the freezing point of the sodium chloride. So it would melt sooner. The lower the freezing point, the sooner it's going to melt. Now in this last one, we have 50 milliliters of 0.5. So we have the same number of moles. So moles, if you rearrange that molarity, are going to be liter time molarity. So they both have the same liters. They both have the same molarity. So our moles for our glucose are equal to our moles for ammonium hydroxide. Now, honestly, this is not the best example for a reason we'll learn in the next unit. So I'm going to change that. We're not going to use ammonium hydroxide. Instead, let's use strontium hydroxide. So if you would change that for me, please. Okay. Now, glucose is covalent. And remember I said, if it's covalent, I is equal to 1. It does dissolve, but you'll get one glucose that was a solid, and when it dissolves, you'll get one glucose that's aqueous. It hydrogen bonds with the water, but does not dissociate into ions. For strontium hydroxide, I is equal to 3. So since this has a bigger I, if we go back to the other one, right, compared to I equals 1, I equals 3 is greater. Okay, hopefully this gives you a good qualitative understanding. If not, you need to talk to me right away in class, and I'll do another little mini lecture on this. Until then, this is your very best chemistry teacher, the one who loves you the most, signing off.